Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 36 and we will be studying this time SOI MOSFET, which is silicon on insulator MOSFET, and we will also look into partially and fully depleted silicon on insulator MOSFETs. So, this is the class 2 which we will be looking into. So, the outline of this talk will be why we are using SOI technology. So, what is the motivation for SOI? SOI is, as the name suggests, is SOI is basically referred to as silicon on insulator, which means that if you remember when we were doing bulk technologies, which means the CMOS technology or even bulk MOSFETs when we were doing, I had a substrate, right? I had a substrate, and in that substrate was basically a semiconductor, maybe a p-type semiconductor, followed by a thin oxide layer, and then you had metal gate here and oxide and everything was there, a source drain at this particular point. This is what we have done for so long. Now, we will see in the next slide, few slides, that as the name suggests, I need to grow an insulator, a thick insulator on the back side of the device in order to do some changes in the output characteristics of the device. So, we will look into the limitation of the bulk technology and then advantages and challenges which we face in SOI, and then we will look into the SOI fabrication process, right, or the process flow in the fabrication. So, SOI technology refers to the use of a layered silicon insulator, silicon substrate in place of the conventional silicon in semiconductor technology. So, if you look at the conventional bulk technology, this is my conventional bulk technology, right? The conventional process, CMOS process or the MOSFET process, where this whole area is basically silicon. Right? This is my silicon. What we have done here is that there is a thick layer of silicon dioxide which is introduced between the silicon substrate and the floating body. So, this is basically a floating body. Why is it referred to as a floating body is that this is not connected directly to any external potential, right, neither to VDD, not to ground, not to any place, and therefore, this silicon which you see, the p-type silicon here, is referred to as a floating body at this particular case, and this is basically an insulator here. This is basically a thick insulator, also referred to as a buried oxide. So, you have a large buried oxide here, thickness is very large, and there is a silicon substrate at the back side. So, you have two silicon substrates separated by an oxide layer, right, and then you have of course the source, the gate and the drain at this particular place. So, silicon on insulator, which is SOI, refers to the use of a 3-layered substrate in place of a conventional silicon substrate, right. As you can see here, a thin layer of silicon is placed on the top of the insulator, such as silicon dioxide, which is in this case, and also known, this is also, as I discussed with you, it is also referred to as a buried oxide. And the transistors are built upon this thin silicon layer, the upper silicon layer, the transistor is there. Since you are putting a silicon dioxide at the back side of the device, this is what is known as a full dielectric isolation, right. So, this is also referred to as an FDI or full dielectric isolation. Full dielectric isolation. What does it mean? It effectively means that the upper active layer, which is the top layer, is effectively isolated fully from the bottom layer, and therefore, backside leakage current parasitics are much reduced in this case. The type of insulator which you choose, this brown colored insulator, right, this is my thinox. This is thinox, which is thin oxide, and this is thick ox, which is thick oxide, this is silicon dioxide, right. they are quite different from each other, the way they are brought up. The above oxide layer should be as thin as possible, so that gate has a better control of the silicon. The lower one should be technically as big as possible, because if you have to do that, then you ensure that the leakage currents and parasitics are lowered. Similarly, sometimes also use silicon on sapphire, SOS, right, SOS, for RF applications, silicon on sapphire. Silicon on sapphire can also used, and that is generally used for high frequency RF applications, right, many a times it is used. SOI is also used in places where you require a good amount of radiation hardening, which means that those devices which can sustain large amount of nuclear radiation or electromagnetic radiation, to be more precise, we prefer to use SOI technology, right. Now, as the MOSFETs are scaled down near submicron or even nanometer scale nowadays, obviously, as you can understand, small geometry effects will be taking over. The third point, if you the bullet points, the SOI based devices differ from the conventional silicon built devices, that the silicon junction is above the electrical insulation, typically a silicon dioxide or sapphire, as I discussed with you, below the active layer of the device, and the parasitics are much smaller in case of SOI technology. So, let me show you therefore the schematic which we see. So, I have a gate here, this is a metal gate, right. I have a metal here, and with metal we have connectivity here, VDS. This is the buried oxide which you see, and I have a silicon substrate here, and this is source, drain, gate. So, it is everything the same. Effectively, you have a violet color, the buried oxide being inbuilt within the region. Now, if you look at the conventional, this is the conventional CMOS. So, conventional MOSFET which you see here. How is it different? You have, so your drain in this case is attached to an oxide layer here, your source is also attached to an oxide layer, but in a conventional MOSFET they are directly connected to the substrate, and this substrate is if it N type, it is a P type substrate which you get. So, what happens in this case in a conventional MOS device is you will have a depletion layer which will be formed between the drain, source and the substrate. However, in the case of SOI, this layer of depletion will not be there. Why? Because you are terminating the drain and source by a buried oxide. So, there is no depletion region which is formed here at this case. It also helps me to reduce the leakage current from the backside. Now, this is we have already discussed the first diagram in our previous discussion, but let us go one by one and see how it works out. Now, for continuation of Moore's law beyond 28 nanometer and below, we need to upgrade from our planar technologies to SOI technologies, right, bulk technologies. Obviously, there are large amount of sort of complicated circuits being generated, and therefore, you do not want that the active part of the device should talk with the substrate to a larger extent, in order to reduce the parasitic effect and the off current. And the reason why is it not like that, because you have a diffused source drain at the substrate, right. So, that is the reason it is better. Now, let us look at one advantage of SOI device is what is known as the latch-up effect. Basically, what is latch-up? It is basically, latch-up is nothing but low impedance path between VDD and VSS, because of the formation of PNP and NPN and PNP transistors. So, these are BJTs, bipolar junction transistors, which are which? This is this. So, you see, if you look very carefully, remember your NPN and PNP transistor where emitter was, suppose I am doing an NPN transistor, then my emitter was N type, the base was P type and the collector was also P type. If you look at this structure here, at this structure here, this is nothing but a PNP transistor. Now, why? Because you have this P plus region here, I have an N well here, and then outside I have a P type substrate. So they basically form two back to back coupled PN junction diodes here, and that can be actually enumerated, understood as PNP transistor. Similarly, if you look at this particular point, I have a P type substrate here. I have an N well here. So this is N, this is P, and again I have an N plus region here. So this also forms an NPN transistor. So I have got one NPN, right, and one PNP transistor, right. So one NPN and one PNP. So what happens is NPN, PNP, if you look very carefully, so these BJTs actually form a PNPN structure, right. They form a PN structure. And when you have this positive feedback coming into picture, they tend to short, or these PNP transistors actually do a breakdown, and therefore there is a low impedance part between VDD, which is this point, and ground, this point, which means that this is basically known as latch-up problem in CMOS. Most of this is basically a twin well or a twin tub process, twin tub or twin well process. And in twin tub or twin well process, we have this problem of this thing. So if you put a SOI device here, because of the oxide layer, this PN junction is not formed, and you will automatically get a much better profile. This is one advantage of using a SOI device. Now we have already seen that we are using a full dielectric, and therefore the cap value is reducing, and so on and so forth. Now let us look at the other effects here, and let us look at the two types of SOI MOSFETs available. One is known as a PDSOI, which is known as a partially depleted silicon on insulator. One is known as FDSOI, which is known as a fully depleted silicon on insulator. So this is your partially depleted, and this is fully depleted, right. As you can see here, in the case of fully depleted, you have the silicon substrate to the bottom, but in case of partially depleted, you have the silicon dioxide, then you have a floating body at the top, and then you have the metal layer available with you. So these are the two types of SOI devices which are available. Now PDSOI has got some of the advantages, and FDSOI has got its own advantages. There is also another type of device which is known as UTBB, ultra thin body bias, back body bias, SOI, FDSOI device, right. Now the insulator layer, the silicon dioxide which you see, this does not allow the source and drain to talk through the substrate. So effectively it insulates the source and the drain, right, and that is the reason there that does not form a parasitic capacitances in that case. Similarly, the insulated layer also confines the flow of electron from source to drain in one direction only, and therefore reducing the performance, degrading leakage current factors, right. So if you look here, the PDSOI has got some advantages. The silicon channel thickness is of the order of 50 to 100 nanometer. The buried oxide thickness which you see is of the order of 100 to 200 nanometer, even more sometimes more larger than that. Relatively older technologies had even micron thickness devices. As I discussed with you, we have less capacitance generated and therefore reduced leakage. And one important point is this is much more stable in a sense that if you vary the backgate bias, the threshold voltage will not change too much in a PDSOI device, right, partially depleted SOI device. So it is much more stable to variations in the backgate side threshold voltage. Okay, generally they are used for ultra low power design capabilities because you want the leakage to be as small as possible. Okay, now let us come to the next part of it. That previous one was a PDSOI, now this is a fully FDSOI advantage. The thickness is somewhere which I have written here, the silicon thickness is 10 nanometer. The box is relatively small here, the channel is fully depleted, right, and therefore you have a better control of ability. In the previous case when you had PD, the partially depleted, your channel was partially depleted in a sense. In this case it is fully depleted, right, and therefore there is a greater ability to control the channel in that sense. Now let me come to the drawbacks of SOI devices. There is a big problem which SOI devices face, and this is what is known as a kink effect in partially depleted SOI. What happens is, if you look to your conventional bulk devices or bulk MOSFETs, uh, this is something like this. If you do not consider any second order effects, it will be something like this which you will form. If you plot drain current with respect to drain voltage for various values of gate 1. So, basically Vg1 is less than Vg2, less than Vg3. But what happens here in this case is that as you plot drain voltage with respect to drain current, we see that the current first increases, then starts to saturate, but then suddenly at a particular point or a particular value of input drain voltage, you see a sudden jump in the current happening. This effect is referred to as a kink effect in SOI MOSFET, right. There is a sudden jump in the current which takes place because of certain reasons, right. We will discuss that reasons if time permits, but it jumps. So you see that the output impedance of the device is not constant in this case. It varies drastically from one point to another. In fact, it lowers down as the kink effect comes into picture, right, and therefore I cannot use it as an absolute current source for any practical purposes, because if there is a kink effect, there will be lowering of the effective value of the drain current, right. It will increase, and therefore the resistance will actually fall down in that case. Let us come to the floating body biasing effect. So, if you look at, so body biasing effects occurs. So, when you apply a voltage VSB source to bulk, right, I discussed with you that earlier also in the threshold voltage, VTN will be equals to VTN 0 plus gamma times this value, where gamma is the body coefficient factor and 2 phi f is the bulk forming potential which we say. Now, where Vt 0 n is the 0 bias and gamma is equals to root 2 q epsilon silicon Na by Cox, right. Now, this gives you a floating body bias effect, but if you can see cleverly and clearly in our previous diagram here, if you look in both the cases, the substrate bias has got a relatively almost no control over the channel, and the reason being that your oxide thickness is so large that it effectively insulates the top channel from the bottom biases. Now, with this let me come to the drawback we have already discussed. So, let us now give you an idea about the insulated box layer, as I had already discussed with you, that they are all typically used in analog design with doped channel, and this is an FDSOI, this is a PDSOI which you see, partially depleted SOI. And you can see here, you do in a partially depleted, you have a floating body available with you, right. And as you can see, this is the floating body because of the partially depleted body, where there is no floating body typically in a fully depleted body, because the whole body has been depleted of any charge carriers in that case. This is my spacer region around the two edges, source, drain, gate, buried oxide, and I have a silicon substrate at this particular point. Now, let us come to the silicon on sapphire, just give you an idea, SOS. So, what you do is that, so you prepare a sapphire, have a 112 plane, and over that you put a 100 silicon plane, right. So, this is silicon is grown over the sapphire. Sapphire is typically aluminum oxide over which you try to grow sapphire, right. This is known as a heteroepitaxy process, right, and it becomes a part of the CMOS technique in SOI family. Now, another way of forming this partially depleted or even the buried oxide layer is what is known as a SIMOX, or separation by implanted oxygen. So, what you do is that, so I have the silicon wafer, the green colored is my silicon wafer, and if you see these dotted yellow ones are basically my oxide ions getting placed at that particular point. So, what you do you use an ion implantation machine from an external source and put high energetic ions inside the silicon, right, with a range typically at the place where you want the buried oxide to grow. There you use energy of the ion implantation machine to be approximately 120 to 200 kilo electron volt, and the dose to be approximately 0.3 to 1.8 into 10 to the power 18 per centimeter square. Now, the problem with ion implantation is that you end up having maybe though you are able to implant the ion, but the silicon itself gets high defects. So, we need to do multiple implant to overcome these defect densities. So there will be heavy defect densities when you dose, when you put dose with effective dose with very large energy, right. So the silicon atom itself will start shifting from its mean position. This case is known as SOI separation by implanted oxygen. Psi is S, this is a S, psi, and then MOX is MOX, right. So the SOI is what we get here. This is in SOI technology we use it. As you can see, SOI varies from 50 to 240 nanometer, and typical box thickness is about of the order of 400 nanometers. Another good way of developing a silicon wafer is that if you can put hydrogen dose, typically hydrogen 1, right. You as I discussed with you when I was discussing with you the double gate MOSFET, in SOI also you do a bounding with another wafer, right, and try to make an H2 implant through the thermal oxide. So using through the thermal layer you try to put an H2 implant, right. Now as the pressure of the hydrogen goes on accumulating, the micro cracks and micro cavities which were induced by initial planning of oxygen, they easily split out along with the implanted zone. So wherever in the implanted zone you have those oxide layers and they are tending to sort of break it up, these high pressure hydrogen atoms tend to crack those and they form this layer. This hydrogen peaks sits at this particular location and then tries to break the two together, so that they are separated out in the SOI technology, right. Now I will just quickly go through the process steps here. So if you look very carefully, I have the silicon substrate and of silicon film, I have a BOX. I etch away the silicon film using either any of the etchant species. Once you have done that, I am left with these buried oxide being available to us in form of humps, and these silicons are a form of humps which you can see. Then what you do is that you do a P plus layer and then followed by P plus layer to be generated here. We want this to be an N type and P type together. So this yellow colored is boron implanted, so which means that P plus layer is formed at this particular place. Easier said than done, because boron will actually penetrate into oxide layer slightly, and you need to therefore be very cautious about how much amount of boron species you are inserting and what is the energy level of inserting the boron species. Then after you have done with the P type, you try to do for N type on the left hand side, which is on the left hand side as you can see here, the green colored N type, and then buried oxide here. The final step, what you do a metallization, right, the metallization, and then you try to grow a box layer here, so that this is effective isolation, and this aluminum layer starts to work as the metal for the gate layer as well as the source and drain layer. And this gives you a brief idea about basic steps of SOI. You will get many such diagrams or explanations in open literature, but this is what we get in this case. Now, so let me just give you the advantages while finishing this lecture. Some advantages of using this thing. Let me write down PDSOI, right. PDSOI gives you improved power efficiency, lower thermal footprint, and obviously therefore extended battery life for all portable applications. Now FDSOI dopant uses is greatly reduced, and therefore in FDSOI, since you are using very low dopants, variability issues are almost negligible. So there is no variability issue. Variability means because of process or doping, if there is a small variation, then how does it influence the overall electrical characteristics of FDSOI. So what we have come to learn is that FDSOI is typically having much better reliability in terms of process variability issues. We can generate very complicated analog circuits using these technologies at much lower voltages. There are many techniques used for growing the silicon dioxide dottle. So let me recapitulate what we did for this lecture. We looked into the concept of SOI devices, how is it different from bulk. We looked into PD SOI devices and FDSOI devices, and then we finally looked into its process steps, right. In various process steps we have seen how these things are there and how is it advantageous with respect to bulk technologies. So, with this, let me thank you all for your patient hearing. We will take the next lecture starting from here itself. Thank you.